using the resources effectively. I'll go into depth in a few things now. Running programs, understanding the basics of program execution, compile and optimizing. So here we are actually attacking source code, which I deliberately did not do in the first one. That's why I put up the first one as beginner and this one as intermediate. And using libraries. I also touched upon the people complaining that there's a huge difference with AMD and Intel processors, and this has to do with typically with libraries. Scaling, profiling, memory, and storage while you are running the program. Scaling I showed last time, but this cannot be stressed enough that do a scaling test. Most users that require large amount of quota from the research allocation committee have already presented scaling test. But imagine that you are on the green one running at 100 cores. You are in a very bad situation. So please do scaling test like this one. See if you are on the right-hand side running at 32 cores, it actually goes slower than with 16. You could very, very well be in that situation. So please do scaling test. So it cannot be stressed enough. So understanding basics of program execution, memory, cache, and cache coherence. We already learned now that using the level 3 cache is excellent. And yes, it cannot be stressed that the data, the computation normally needs data. If you get away with that, doing simulations with only could run inside the processor using only the register, we will have a speed that we've never seen before. So, but we have to have data, and we have to get data from the memory, and we have to process the data, and we have to write it out again. And this can be complicated or tricky. It should be simple. A programmer should spend most of the time doing the actual science and not computer science. I mean, most of us have a background in natural sciences and are not computer scientists. And of course, we shouldn't be forced to be computer scientists. But as we already heard, that even climate people are being forced to spend time on computer science, like reprogramming, so you could utilize the level 3 cache in the best possible way. But this is the world we are faced. So, question. I'll answer it shortly so you don't have to think too much. What is the smallest amount of data you can access from memory? Most people that are not computer scientists would say a character or a byte is the smallest amount you can request or access from memory, which is correct. But when you request 1 byte from memory, you are actually requesting a whole cache line. Imagine there are 64 seats on the bus and you are using only 1. There could be 63 more people with you. So if you are only requesting a short or a character, you waste 98% of the memory bandwidth. But most people of us are not dealing with characters. We are dealing with double precision numbers or 64-bit numbers. Be careful with using the double precision, because in some cases that could amount to 128 bits, and 128 bits numbers goes very slow. So I tend to try to specify 64-bit precision every time I talk about double. Double means normally when I talk 64-bit, but don't trust that forever. It will give you only 7/8 of the memory bandwidth. And since memory bandwidth is a limiting factor, we should try to spend it as wisely as possible. So this is a bit of computer architecture. This is computer architecture, computer science for the non-computer science. If you have background in computer science, this might be childish. We request memory cell number 7. And we pull the whole cache line in. We copy the memory cell into the register with the character A, and we're happy. So this is the instruction load A from memory 7.0. It should actually be a parenthesis around the 7 for that instruction. Anyway, doesn't matter. We carry with us the whole cache line, but we are only using one. So in principle, we should use all the data that we pull in, and this is the compiler's job to do for us, because then it's not so easy to program. But if we program well structured and have arrays that are and access the memory chunks in a stride one, where I mean that we do consecutive 1, 2, 3, 4, etc., run through loops in that way, and mix up the loop and do the data structures rightly, we might utilize all the cache line when we first have pulled it into the processor. Then, but I mean, there could be a semester worth of discussing how to use the cache and so on, and even more, it could take a lifetime to play with that. But just to show a quick glance of how hard this is. Then we have the cache coherence. A user can be sure that all memory locations are updated. So you don't really have to think about the cache coherence. It's a hardware thing that fixes the things for you. But when I do teaching for more for a longer course, I have an example called false sharing, which is actually takes much longer time using 2 cores than 1 core, because you access the same cache line from 2 threads and 2 different processors or 2 different cores and 2 different caches. If they are sharing the cache, it's okay. If they are not, it's not good. So this is the cache coherence problem in some way. We are reading the same A into 16 different cores, and we are assuming that they are not sharing any caches. They could very well do, but we assume that they don't share any caches. You see, they all have the same copy of the cache. Everything is quite good. So we can we can read the A, but what happened when we update one cache line with the B? Core 16 might read the memory cell that the B account for. Like the B would be in memory cell number 9. So if we are on core 16, the lowest one, and ask for memory cell number 9, which we know is in the cache. So the hardware is set up in such a way that when we write to the cache, the B to a cache line, it sends out a broadcast message. There are several ways of doing cache coherence, and cache coherence is generally quite complicated. So we can just say that to put everything behind the scenes, that it's broadcast a message to all the other cache lines that they have a flag set that they are invalid. So if we want to read from memory cell number 9 on any other core, let's say core 0 or core 16 or whatever, the hardware will trigger a write out of cache line from core 8, which has updated the memory cell, write it out to the memory, and then my cache line at 16 need to be read in again from the memory. And you can easily understand that if you are doing this wrongly, you could spend all your time reading and writing and invalidating and validating cache lines and make it a nightmare. It's easy to write such a program. You can do false sharing, which you are doing 2 threads that run. It looks very nice. There are no overlapping, no race conditions. Everything is perfect, except that you forget that those 2 variables are so close in proximity in the memory that they are probably sharing the same cache line, and you get trashing of the cache. So I'm not trying to teach you to be computer scientist, but it's something that you should have at least have heard about and have some kind of knowledge about cache trashing, because it can happen. And it manifests itself that a serial program is faster than a parallel program, like typically OpenMP or threads. It's not a simple thing. And even more so is this one. There are cores, there are logical cores, there are virtual cores, there are physical cores. So what is a core? It's a very, very good question that is very, very hard to answer because it's not easy. A modern processor runs a stream of instruction that can call a thread. The simplest way, thread is a stream of instructions. You can easily see that on this block diagram, there is a lot of boxes. And that instruction thread goes into one box, which is not here, but it's decoding. And there are general more than one decoding unit. And so the square box here can actually decode more than one thread. It can sometimes 2, sometimes 4, depending on the processor. Some can even do more. Some ARM processors that are for computation do 4. Some power processors do 4. x86 normally do 2. So they can decode and take in, run or decode at least, and run 2 threads at the same time. And from a programmer's point of view and from the operating point of view, these 2 threads can be seen as 2 cores. So they actually manifest themselves as 2 different cores because you can feed them with 2 threads. So it looks like 2 cores. And it shows up as 2 cores. So they are referred to as virtual or logical. But there is no such thing as a physical core because the physical core has the capability of doing 2 threads. So each so-called referred to as physical core can be 2 virtual cores or 2 logical cores. But it can run and accommodate 2 threads. But problem is that if you run 2 threads into this one, and they are or more or less the same, like in HPC where we do structured problems, you request the vector units and the floating point units that are not duplicated. So these 2 threads might compete for the same resources within the hardware, which means that it might be slower to run 2 threads competing for the same hardware than one that do not compete with the hardware. So it's a trade-off. Generally, it's better to turn the hyperthreading or the logical cores off, or setting the SMT to none. And this is done in some systems, and some systems have the SMT to on. But in most cases, it's beneficial to turn it off, or we can do it manually by only schedule 128 cores or jobs or ranks or threads or whatever at a system like Betsy. Or other one, do not ask for more than there are. So if you have 40 physical cores and then 80 logical cores, do not run more than the one you have so-called physical cores to. Do not schedule more than 1 thread per core. And how to do this is also a bit tricky. But the point is that these logical cores are only a way of dealing with the fact that each of the cores can actually schedule 2 threads on the same. If we, on the other hand, are running a mixed workload like office work, web servers, or a lot of other things, then the workload and instructions comes in a very mixed way and a whole variety of instructions. So you can see that you have both an integer unit and a floating point unit. So if one thread is scheduling only floating point instruction, the other is only scheduling integer instructions. They can run simultaneously. So you get twice the performance. And it's also a way of hiding memory latency, but that's another different thing. But the point is now it try to explain you the difference between the logical, virtual, and physical cores. It's not easy, but the practical offset is that in HPC it's better to either turn it off or do not schedule more than one thread per core. I know this is a hard concept, but we cannot spend the whole time discussing it, so I'll just go on when we. The other thing is that not all memory is equal. Some memory is more equal than others. A memory is divided into banks or nodes. And now there's another use of the word node, and this respect inside the compute host, the memory banks are referred to as nodes, just to confuse you as much as possible. Memory is divided into a set of nodes. In this simple case, I have two CPUs, or two CPUs are normally also, as somebody pointed out yesterday, a CPU is also referred to as the chip, and in this case there are two sockets. Each has a chip in itself, and that's it. So each socket has two memory attached to it, two memory banks attached to it. There is an interconnect between the two sockets on the motherboard, and the other socket has two memory. We have 4 memory banks in all. And all this memory is visible from any core, can see all the memory, but you can easily understand if you sit on the upper CPU and request a memory cell in one of the memory on the lower one, it will take longer time and has less bandwidth than if you are accessing the memory attached directly to your socket. So the NUMA stands for non-uniform memory access, which is exactly what I explained, that the memory is not symmetrical. Memory is such that some memory is more equal than other. And this have implication for performance. How this is done, you can run an LS CPU and see the memory node. You see here the 0 core is the memory node 0, and the number 64 is on memory number 4, and you can see that 192 is also on 4, and 255 and 127 is on 7. I have a better map later on, but this is a simple command that you can run. It will print out 256 lines. So you can play with the LS CPU on the different system and check it yourself. But there are other ways of checking. We can do NUMA control -H and print out. It will print up a bit more than this. But here we'll have a map of which cores that are connected to which memory bank. So the point is that when you're running typically shared memory jobs, is that you try to allocate memory only on your local memory, which is again computer science and what a normal natural science user shouldn't really have to deal with. But in order to get the best performance, we are forced to deal with such things like this. So scheduling the threads on local banks is important, and the way we can do this is to fix the threads to run on only the cores that are attached to the local memory. The simple way of doing is using NUMA control and setting it to -L local, and that will try to allocate memory on the local memory banks. But this is a map of how the cores are laid out, and we can easily see that, and there are 2 threads per core on the Betsy systems, because they go all the way up to 256. So, and you can also see which memory cores, which cores that are attached to which memory. So we can run something called HTOP, which list out. So here we can see that the ranks are distributed on both sockets, because 0 to 63 is socket a socket 1, no 0, and 64 to 127 is socket 1. So we are using both sockets, full performance. Hopefully, memory is allocated correctly so that it's only the first socket is only allocating memory on the first socket, and the other one is also the socket 1 is also allocated memory on socket 1, and that we have put in binding so that a thread running on socket 5 will stay on socket 5, because if it jumps over to another core on another processor, the memory might not be local, and that impacts performance. Here I force it differently. Here are another one. It looks like we are using 128, but I've scheduled them in such a way that they are only running on the first socket. So the 128 threads are allocated to the first socket and effectively half performance. So be careful. You can also look on the memory, how memory is allocated. This is the two different ones. The first one shows that there are very little memory free on the first 3 nodes, so the first socket. So the job is only running on the first socket, not on the other. If I, on the other hand, schedule on both sockets, means all 8 memory nodes, you see the memory is more or less average. Socket number, no, core number 0, and the first core is normally runs operating system processes and such. So the first NUMA bank is always lower. It's not always, but very often lower than the others. But this is a way of life. But you see, it's spread out fairly evenly. And this is the performance you get. It's hard to get it better, but yeah. But the good thing is that if we don't do anything, we'll get this. And if we are looking carefully, we'll see that the black parts here are filled up with black parts from the other one. So you see that it should these should be 2 side by side. And if we move those, if we split it in half and overlap them, you see that both columns will be filled. So asking the operator or letting the operating system dealing with this normally makes it reasonably okay. This is done with the Intel MPI, and the defaults are quite good. Intel is famous for doing things, a lot of optimization per default, which is good for 90% of the users and bad for 10%, but they claim that it's better to having the defaults best for the majority of the average users. So if you don't do anything, it's normally okay. But it's important to have a look, and you can easily log into your node and have a look. This is a Wharf example. So you can log into the node, start HTOP, and look how the cores are and the ranks or threads are distributed on the cores. Again, we are dealing with the storage. We are back to the problem of flying east or west to Bergen. And as you saw, most people tend to fly east instead of going west. So it's a long, long way. And you saw that only 0.8% of the jobs are using the NVMe RAM for local scratch. This is another thing that I run on the local system here in Oslo, the Fox system. Here I schedule 128 IO zones on the ESS is the IBM Elastic Storage. So it's using the GPFS file system, and it's quite nice storage system. you see that for random read, it's nightmarish. And you see that for random read, it's quite good for using the NVMe. The login node has PCI Express version 4 on the NVMe RAM, so it's slightly faster. And the normal compute nodes has less performance on the NVMe. Random read is interesting because they are actually exceeding the bandwidth. So it shouldn't be able to do that. But we discussed this morning and figure out that when you are doing random read alone on a system with a lot of memory, I requested the test here twice as the memory, but as you read in random chunks of data from the disk, it cache in the memory, so the memory will fill up. And if you are doing random read, there is a possibility that that sector or block is already in the memory. And I think that's why we get more than the actual bandwidth on the disk on the random read. Again, we can see using local storage or parallel file system. So this is also on the Fox system, but the same thing applies to Saga, where you have the possibility of using the NVMe RAM as a local scratch. If you are doing sequential read and write, it doesn't really matter that much, but if you are doing any kind of random, it's a huge gain. As I said in the earlier slide, 20 hours versus 47 minutes. If you are only doing sequential, the benefit is not that big. As you can see here, it's 1 or 2, it's comparable. So another thing with the file system, it looks like the one with the cache. We have all of the systems we have BGFS, we have IBM Global Parallel File System, we have Lustre. They're all parallel file systems. There's a POSIX file. I used to refer to as a file as a tape. You can read and write to the tape. You can spool it back and forth because it's easy concept. There is a marker. When we open the file, the marker is at the first byte, and then we can do a seek and we can write, or we can start writing from the start. So for a tape, we can start writing. The tape will rotate slowly and we can write. And we all see on movies, old tapes, that they spin in a fast way, then they stop, then they do some shoe shining of the reading heads, spooling back and forth, and then they start going slowly, and then they start going fast again. This is actually when they are issuing read, write, and seek. Seek is when they ask to go a million sectors ahead, then they go very fast, and then they do some shoe shining to figure out where am I, and then get to the correct sector, and then reading or writing. Same thing is on the file, except that the file is on a hard drive, and the hard drive has heads and so on, and that we don't see. So the tape is a much better example to illustrate this. Point is that there is a write token handed out to the first one who asks to write on the file. So you have the write token. All of these nodes have opened the file and want to do write, but only the one who have the write token can write. All the others have to wait on a single POSIX file. So this is problematic for any parallel file system, that you cannot write in parallel unless you do some tricks. And that's not often done. There is a way of dealing MPI IO on some file system. If you are doing global parallel file system from IBM and using IBM MPI and so on, you can write at the same file in parallel. But normal POSIX file is not so easy to write in parallel simultaneously. So you have a write token, and only the process who have the token can write. The other can read, but then again, you can have race condition. You read the sector. Is it already updated by the node or is it not? It's not so easy. So parallel file system is not simple. So that's why there are a lot of problems with the file system. You see, if you ever hear about file system problems and so on big system, it's generally the parallel file system who has issues. Then this is what we normally do with running. Now we are open up. Another concept is that compile and building and optimizing program. This is a talk by itself, and we have 15 minutes left. And I will just briefly touch upon, but there is some things that you can pick up. You can ask the compiler for help. The only time the source code is parsed and analyzed, the compiler actually, it doesn't, using the word understanding is hard, but the compiler actually need to partly in quotation marks and partly understanding quotation mark what you actually want it to do, because it has to translate the source code into assembly instructions, which is like typical load A with B and add them together and so on and store the result in the memory. So the source code is actually analyzed, and is this only time it's actually analyzed in a timely way. So the compiler parses your source code, try to translate it, and can do some optimization, but it can also tell you what it could and what it couldn't. And you can read the documentation in the just issuing help, or of course the online manuals, but there are thick books about this. And to make it worse is that we are faced with parallel on many levels. First of all, we have a vector. A vector instruction can do 8 or 4 double or single precision numbers in parallel at the same time. It can actually multiply 4 numbers together in one clock cycle. So vectorization is some kind of implied parallelization within the processor. Then we have several cores. We already learned about OpenMP, and we have multiple threads. So within each processor or each socket, we have up to 64 threads. So first of all, we have the CMD with 4 or 8. Then we have 128 threads in a single node. And then we employ multiple nodes on top of that with MPI ranks. So we have at least three different levels of parallelization here. We can ask the compiler to optimize our code. This is a simple compute pi program. We can turn off if we don't do anything. The Intel has some good optimization set by default. So we get 5 seconds, 5.7 seconds. We turn off the optimization by issuing O0. We see that we get 16.8 seconds. This is without any optimization. So this is what the compiler do if we ask for 0. If we do minus O3, which is even more optimization, we do O fast, same. If we do O2, so there's no difference between O2 and O3. And we put in OpenMP SIMD. SIMD usage of SIMD vectorization instruction is also by default. That's why you get, if you don't do anything, you see all the defaults get you to 71. And then I wanted to check, does the vectorization have any impact on this one? I get 7 seconds, so its vectorization is important. Sometimes you can have problems that are vectorized much more. But even here, you can see that vectorization is important. Then we can fool the machine. This is run on Betsy. We can fool the processor into accepting. No, this is okay. You can use M architecture core AVX2 that works also on the AMD directly, and we can use the AVX2 vector unit. Intel doesn't, the Intel compiler doesn't put this on this processor because it reads what kind of processor it have, and then it uses the SSE vector instruction unit. So I've asked it here to use the AVX2 vector instruction, which is twice as wide as the SSE. And then I get down to 455. So this is just a simple compute program, pi with one loop. So you can imagine a whole climate code with millions of codes. It's not easy, but the compiler can help us a long way. But be careful. optimization might necessarily be safe. If you do arithmetic with pencil and paper, you know that A times B is the same as B times A. Assume they are numbers. And computer arithmetic is not always as nice as we would like it to be. So if we are multiplying two numbers together, it's generally okay. But if we are doing more complicated stuff like A times B plus C and so on, and the compiler shuffles the operands around, the result might not be totally accurate. It's generally accurate, but not totally. So if you are very concerned about numerical precision, it might not be safe. And many people are dealing with this. So I've seen many examples where people use precise and so on. There are some models that you can put up. And you see, if you put on fast, it enables no precision division. So they do division is so hard that it's very complicated, and it takes a very long time to divide one number with another number. So it can with a slightly lower precision, and it's much faster. So be careful if you are concerned about the numerical precision. So this you have to read the manual just to show you that things are the way they are. Then the vector register. You see that if you can fully vectorize, you can have multiple lanes doing it simultaneously. So if you are dealing, there are 256-bit or even 512-bit in a register, and that good if you fill it up with characters, you can do or short or integer, you can get very high performance using the vector units. And with floating point numbers, you can have either 4 or 8 floating point numbers in 256. Some of the Intel processors have 512, but experience have shown that if you run those at full speed, they heat up the processor so much so it clocks down. So it's actually more beneficial to run it at 256. And the AMD processor have 256. And
you have three more minutes.
Yeah.
Sorry, we are like.
No, it's not that much left, so that's fine. I have compiler options that you can see. You have opt report. You can see that the defined region was parallelized because I put in an OpenMP. This is the famous Pi example. I used in SIMD reduction. I asked him to ask the OpenMP to do SIMD also. And you can see the SIMD loop was vectorized. So the opt report here generates this text for us. This is the one, the opt report is the one I see that the compiler tried to understand what's going on. So this is fairly important to put in Q opt report and actually read the report. Again, the parallel program you doing Pi, loop was vectorized conversion from interval will be emulated. So there's a lot of information in the opt report. It might be very long, but like this, loop was vectorized, and parallelized. So you can see you get a lot of information, especially if the loop was not vectorized or not parallelized. You will have some hint why it isn't and go back to the drawing board and reprogram. So parallelizing libraries is only a couple of slides. Computers generally do two things. They either do linear algebra or Fourier transform. Use libraries if possible. This is the message to take home. The Intel math kernel library is widely used. There are some issues with the AMD processor, which can be overcome, or you can use another library if you are doing linear algebra. You can see if we are lucky, we can get tremendous impact of performance if we get the compiler to do it rightly for us. If we use you see if you can get it to do the matrix reference implementation up to 26 gigabytes per second for a single core. If we do the library, we can get up to 48, 47, and 50. And you can see the libraries are the math kernel library can do 48 to 50. The AMD library can do 50, and we can have OpenBLAS do 50. So using a library is essential, and there is nothing to stop you from using MKL, and comparable to the Intel processors are more or less the same. Then there is a problem with the Fourier transform is that the math kernel library is outperforming both FFT and the AMD library. I don't know why they have put so much effort into the Fourier transform in Intel, but they've done a tremendously good job on Fourier transform. So if you are doing a lot of Fourier transform, the Intel library is very nice. And the Intel library has wrappers for FFTW. So you can use FFTW syntax, run it through the Intel wrapper, and use the Intel math kernel library, and you'll get the full performance. That was about in 3 minutes.
Yeah, thank you so much, Ole.